So go ahead and answer this question on a scrap sheet of paper, and then we'll get cooking, get the juices flowing. You got about 2 minutes. For you folks who can't see at home, I do have a Bunsen burner lit with a beaker full of water. It's boiling at this point, but we'll get to this here in a second, Mr. All right, somebody explain what's exactly happening when I have this lit Bunsen burner. Yes, go ahead. Okay.
So that heat is transferred to water. So the heat from high source is above water. So the heat will come.
That's perfect. That's really, really good. Now, what I wrote here, you do not need to write this down, okay? I wrote something to this effect where I'm trying to highlight the important stuff. Because the molecules of the water gain energy, the exothermic reaction of Bunsen burner, blah, blah, blah. This increases the kinetic energy of the particles, aka the temperature, the measurement of the average kinetic energy. If I was going to really make this simple, okay, I have, boom, boom, boom. Let's say that's your Bunsen burner. This is not in the packet, this is a little scrap sheet. Let's say that's your Bunsen burner. Let's say this is your beaker. I'm spelling that incorrectly, but beaker, low temp. Yes. Can you still hear me right now? Oh goodness. Well, virtual folks, maybe all go out and go back in if you can't hear me. If you can't hear me, go out and go back in. Oh, that was really dumb of me. All right. So, now we have the high temp, relatively speaking, the Bunsen burner flame. The low temp, relatively speaking, of the beaker. Off we go. There goes the heat, etc., etc. And here's a question I bet you don't know the answer to. Why does the temperature of the water stop increasing when the water boils? This has been sitting at 100 for like 6 or 7 minutes now. Ooh, look at you. Give it a shot.
Probably the wrong answer from the death.
Okay.
When the water boils, it goes into a gaseous state, so the water can't get any hotter.
Okay. All right. There's something to that. There's something there. Meg, did you want to add a little something? Or are you going to say the same thing? About the same thing? Okay. I had one person guess like, oh, well, if it stops going up at 100, is that just because the flame's also at 100, so there's no high or low temp anymore? It's just all the same? That's actually a really great guess. But this flame is way above 100 degrees.
I know water.
Oh, yeah?
Water evaporates.
Well, the water is evaporating. That's definitely true. But the liquid water itself is just stuck at 100. Like this thermometer is in the liquid water.
But if the liquid water turns to not liquid water, then does it get hotter? Or does it get...
I'll say it can. I'll say it can at least. Ian?
Does it cool?
It might. It depends where it lands. Yeah? It can't hold any more heat. Okay. We're throwing out thermochem terms here. Okay. 4.18. Is it 4.18? So I'll say kind of yes to all those things you guys just said. We're sort of circling around. If like the bullseye's in the center, we're hitting all the way around the bullseye. Not quite on the bullseye, but we're in the neighborhood. We're in the neighborhood. You'll know the answer to this question before we leave today. Okay? All right. Now we got to take our phase change notes, thermochem notes number 4. This is in your packet, so now we're in the packet. Now we're in the packet officially. This is what the front page looks like right here. Boom. Yep. There we go. So that's definitely why you want your packet today. Okay. I'm looking at that face. I'm like, I wonder what that means. Oh goodness. All right. Mr. Blaze, I got one more extra, I think, if you desperately need it. This class. We got to talk about solids, liquids, and gases real quick. Okay. So, solids, the particles are in fixed positions. Ooh, the particles are in fixed positions. Okay? They're really close together, and they are shaky. Okay? They're really close together and they are shaking. So these are kind of going to take under the solid section at the top there. So again, this is what the notes handout looks like, this guy right here. I will tell you what to draw in a box here in a moment. Yep. So you may remember, I think I mentioned this before. Okay, so if you look at my fist right here, let's pretend this is a particle. So it's shaking, okay, it's vibrating. Is it really going anywhere though? No, that's what solid particles are doing. They're moving, but at the same time they're not really going anywhere. They're just sort of shaking or vibrating. This is why when you lean on your desk, your hand doesn't go right through it, okay? Because those particles, the solid particles, don't really go anywhere, so they're still just underneath your hand. You can't really push right through them. They won't move. Generally speaking, solids have pretty low kinetic energy. Pretty low kinetic energy. Let's see what the temperature is now. Oh, still 100. Great. It's not going to change. It won't. If it does, then we got to go back to the drawing board.
I'm pretty sure I did the right answer.
I don't know.
He's kidding.
If we draw the box, if I'm looking at the box in the top left-hand corner, so maybe I label this with a little S for solid. Oh, goodness. S for solid. S for solid. I might just draw a few dots pretty close together, like in a corner somewhere. Okay? So they're not going to spread across the bottom. They're not really moving. They're pretty close together, something like that. Now, if I start talking about liquids, liquids are pretty close, like solid particles, but they can kind of slide past each other a little bit. They can kind of slide past each other a little bit. Okay? So liquids are sort of like when the bell rings and you go out into the hallways. There's a lot of people there, but at the same time, it's not like Gozer's like, oh, runs into a person, oh, runs into another person, oh, sorry, Stacy. Like, it's not like he's constantly running into people, he's just sort of sliding past them. So there's a lot of people there, they're close together, but at the same time, they're just sort of sliding past each other. Does that make sense? So that's what the particles are doing in a liquid. You can't compress a liquid, okay? So this Erlenmeyer flask on my desk has about 400 milliliters. If I were to pour those 400 milliliters into this beaker, yes, the liquid would change shape, but it would still have the exact same volume of 400 milliliters, okay? So you can't compress the liquid, you can't squeeze it to a smaller shape, you can just sort of change the shape, but it will always have the same volume, okay? Because those particles are already pretty close, you can't really squish them any closer. It has some kinetic energy. Solids have really low kinetic energy. Liquids are sort of medium flavor. A little medium. And if I'm drawing that box for liquids at the middle of the top, maybe I'm putting an L right there for liquid, I'm going to draw the particles pretty close together still, but they're going to cover that whole bottom. So maybe solids, it's like you toss an ice cube into that box, so it sort of just stays in the corner. But the liquid will sort of spread across the bottom, but it'll still be pretty close together in terms of particles. And then lastly, the gases. A lot of this probably won't be a surprise. Particles move independently and rapidly. Okay? Think of it when you're at a homecoming dance and it's as if the beat just dropped. Okay? Right? This is where everyone's freaking out. They're going in random directions. They're like flipping out. Okay? That's what gas particles are doing all the time. And it's not like they do a couple of laps and like, whew, oh man, need a water break. It's like, no, gases are just always sprinting around the room or container, whatever they're in, smashing into walls, going in random directions constantly. They'll expand to fill the available space. So every time you breathe out, you're throwing some CO2 out to the air, and that CO2 just goes in all directions right when it comes out of you. So every little nook and cranny in my room has gas smashed up against it. So for example, I don't know, like that corner right there, when was the last time anyone actually physically touched that corner? Probably years. I have no idea. I've never touched that corner up in my room for any reason. But I assure you, there are millions and millions and millions of gas particles smashed up into that corner. And that one, and that one, and up in the vents. Like, the gas will just spread as far as it can in the container that's given. Okay? And it has a lot of kinetic energy. Like a lot. Like so much. A crazy amount. So liquids, you're slowly moving. You're passing people in the hallways. Gases is like Mr. Pilcher. 7 years old. He's in the candy aisle at Kroger without parental supervision. Okay, that's just freaking out, running against the walls. You know, it's going to be craziness. If I'm drawing that box for gases in the top right-hand corner, I'm putting like 5 particles in that whole box. Okay, they're really spread out. They're filling the whole container. Might even put little motion arrows on there, be like, whew. They're going random directions. Maybe this guy's got a bank shot thing going on. Doink, doink, doink. I don't know. Okay, that's what gases are doing. They got a lot of kinetic energy. And when I say they have a lot of kinetic energy, that means, generally speaking, their temperature will be higher, because temperature is the average kinetic energy of a particle, right? Good times, good talk. Things are heating up, pun intended. Let's talk about phase changes. Let's talk about phase changes. So a phase change is the conversion of a substance from one physical state to another. You're going from one physical state to another. Oh yes. Oh yes, yes. Good times. Here are all our labels. I really hope and believe that most of these labels are not plot twists for you. I don't think John's going down here and be like, since when is going from a solid to a liquid melting? I've never heard that term in my life. Okay? I'm like, well, I think you have. Liquid to gas is a little less familiar, but it's called vaporization. Gas to a liquid, so we're going on the same street but the other direction. That's condensing. Okay, it's when you have something condensed. And real shocker, liquid to a solid is freezing. Hence your freezer takes liquids and makes them solids. And the fun one though, when you go from a solid directly to a gas, no dropping off of the liquid stop in between, but straight up solid directly to gas, it's called sublimation. Sublimation. That's a fun one. Like dry ice. If you ever had dry ice before, it goes straight from a solid to a gas. That's sublimation. It's subliming. Okay. All right. Boom. Here's the answer to our question at the beginning of class period. This is the very important at the very bottom of the page. So at the bottom of this page. During a phase change, there is no change in temperature. No change in temperature during a phase change. This is a big idea. When water's boiling, it's at 100 degrees. When it's been boiling for 30 minutes, it's at 100 degrees. When it's been boiling for 30 hours, it's at 100 degrees, okay? It will always be at 100 degrees while it's changing phases from liquid to a solid. Why is that? Because all the energy is being used to change the state. There is a cost. If you want to heat something up temperature-wise, there's a price in joules. Remember heat energy? There's a price in joules to do that. You want to make something increase temperature by 10 degrees, you have to pay the joules. Similarly, if you want to take something from a solid to a gas, solid to a liquid, liquid to a gas, whatever, you have to pay the joules to do that. So on this graph, okay, we have temperature on the y, heat being added on the x. Right here, where the temperature flattens out, it's not changing at all. And right here, the temperature flattens out, it's not changing at all. Those are both phase changes. Those are both phase changes where you must be going from one state of matter to another. Boom. So the answer to this original question right here, why does the temperature of water stop increasing when the water boils? You do not have to write all this down. I will highlight some things that might be helpful. Again, this is not your notes. This is just sort of like, you know, you jot down as a little scrap note or whatever. Once the water reaches 100 degrees, it has reached its boiling point. And it's now changing state. So heat's going in, temperature's going up, 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 up. The moment it hits 100 exactly, it starts to change state. And at that point, all the energy from the Bunsen burner that's going into the water is no longer being used to change the temperature, but it's changing the liquid to a gas. So when you're changing state, all the added energy is changing the liquid to a gas. It's not changing temperature anymore. Not changing temperature anymore.
So in a sense, I was right.
I don't remember what your answer was. What did you say?
That was going from a liquid to a gas, so it gets energy hotter.
Yeah, that's kind of right. Yeah, because you're like, okay, the liquid can't get any hotter, so it's sort of. I think what you used one term. It was like can't contain that much heat or something like that. Was that?
What about 4.18?
4.18 will actually tell you exactly what the price is, so it is related. It is related. So, and which we will be doing. We'll be calculating the price of these soon. We're right. Mic drop. You were about to label the goodness out of this graph right now. Okay? So it's on the back of those notes you were just taking. A quick mic check. Hey, Lexi, can you still hear me? Pizza roll's not full of burger, though. I'll take it. All right, good. Wonderful. Just want to make sure people can still hear me. Okay. So, on phase change graphs, you notice the temperature's on the Y. It'll either say heat added here or just time. But either way, you're adding heat into the system over time on this particular one. So, you'll see the sort of same shape where it goes up, flat, up. Or it might be the reverse where it's like down, flat, down, flat, down. So we're going to label exactly what's happening on this graph. And we're going to go up the graph first, and then we're going to think of it in reverse order. So down here, okay, a couple of labels you want to put. This first flat part, this is water. This isn't true for other substances, but for water, this first flat part will be 0 degrees. And the second flat part, all the way up here, will be 100 degrees, which is very convenient. Okay, so when you are below 0 degrees and you're adding energy to this ice, is what this would be. This is just your solid warming up. This is just your solid warming up. That's all that's happening in this first section. The solid is just getting warmer. It's still a solid. It's not melting at all. It's just getting warmer. It's just getting warmer. The moment right here, this moment that you hit 0 degrees Celsius, that very moment, the solid ice will start to melt. It will start to liquefy. And so this whole time when you're melting, that whole time when you're melting, the temperature is stuck. Holy goodness. My smart board is having a hard time. The whole time when you're melting, come here, you're at 0 degrees Celsius the whole time. There you go. So this whole time you're melting, you're trapped at 0 degrees Celsius, all along this flat line. So the moment the first shard of ice starts to melt, to the moment the very last piece of ice melts, it's stuck at 0 degrees. Now, once that last piece of ice melts, then all of a sudden the temperature is going back up, and you just have a liquid warming. You just have a liquid warming. But from here to here on the graph, those 2 points, the temperature does not change at all. Right about here you have half. Right about here you have half ice, half liquid water. Temperature still staying the same. Now, so the heat's being used to raise the temperature 0 degrees, 10, 20, 30, 40, 60, 70, 80, 90. The moment you get to 100 degrees, okay, the moment you get to 100 degrees right here, now this liquid is vaporizing. It'll be trapped, or you can say boiling, and you're trapped at 100 degrees until every last drop is vaporized. So this right here, this would stay at 100 degrees until the very last drop vaporized. And the moment that last drop vaporizes, which is right here, then the heat energy will go back into warming or heating the temperature up. And so you have gas warming right here. As we go from here to here, Mr. Ford, is energy going into the system or out of the system? It's going into, yep. So as you go up, talking about an endothermic process. It's an endothermic process as you're going up. Let's go down the slide. As you go from, like, I don't know, 200 degrees Celsius all the way down to 100, that means you must be taking the energy out. So energy must be going out of the system. And so that's just gas cooling. That's just gas cooling. The moment you cool the gas to exactly 100.0 degrees Celsius, then it will start to condense. And that gas will condense and condense and condense until every single little gas particle has now become a liquid. And at that point, again, that's 100 degrees. At that point, the liquid starts to cool, and you drop from 100 down to 0, at which point it begins to freeze. And once it's all frozen, then we're back to solid getting even cooler. And if we're going up the graph, that's endothermic. As we go down, the temperature is going down. It must be exothermic. Energy is leaving that system. Energy is leaving that system. So in summary, there are 5 main sections of the phase change graph. 1, 2, 3, 4, and 5. So you have 3 slopes. 1, 2, 3. Even if you're going up or down, and you have 2 flat parts. 1 and 2. And the 5 different parts of the graph. So that's that. Now that would bring us to this right here. So you'll notice that this has the 5 parts, but they're just not labeled perfectly. They just have A, B, C, D, and E. You'll have a lot of questions to answer about this. Here's what I want from you first. I want you to go get your 3-question quiz knocked out on Schoology. And once you do that, I would like you to take care of this worksheet right here. You probably won't have quite enough time to finish this in class, but you should get close. You should get close. You virtual folks, go take care of that 3-question quiz. Virtual folks, the answer key to this worksheet on my board is in the Monday folder. You guys can check that too if you want. So go ahead and get that taken care of. There is no class tomorrow for anyone. There is nothing in the Tuesday folder. No need to open it. Just make sure you take care of Monday's business. And then Wednesday, we're going to do some review, and we're going to do some math review to get ready for the quiz on Friday. Okay?